Good morning. I'm gonna need to get like a desk lamp here. It's starting to get dark in the mornings now. Yeah. Um, so let's just take a quick peek at the syllabus together and then we'll start on our on chapter 3. So share screen with y'all. So just so that we can, sort of be on the same page, at least in the beginning here. I won't always go over the syllabus, but for right now. Okay, so we're sitting here at week 3. So we didn't have class on Monday. You did have an assignment due on Sunday, though. Hopefully you got that turned in. For this week, you're going to have experiment 2, physical separations of mixtures. And then you're also going to have quiz 3, the quiz that's associated with the physical separations of mixtures. And then you'll have a mastering chemistry chapter 3. So hopefully we can get through all of chapter 3 today. Maybe not. If not, that's okay. We can smush a little bit of it into next week, and then we'll do chapter 4. Looking forward, we can see that our test 1 is going to be on that Sunday, the 20th to the 21st. Now, if for some reason we don't quite get everything in here, I do have the flexibility to move that exam, but I usually am pretty good at being able to squeeze stuff in. So right now that's when the test is set. We'll try and keep it there. So, all right, so let's get into chapter 3. Last time we finished up talking about density, correct? Yeah, okay. And then we were just done with that. Yeah, we did a bunch of example problems on that. That's what I thought. Okay, so this chapter, until the end of it, is going to be a little bit of a relief from mathematics, which some of you may like, some of you may not. I always liked the math. I always felt like I didn't have to memorize anything. I could just like solve the problem. But here we're going to get a little more concept based. So I'm going to close up some faces. Bye guys, I'll see you in a little bit. And talk about chapter 3, matter and energy. So atoms and molecules, they're all around us. Yes, we've talked about that. Everything that you can see is matter. What do we define matter as? It's defined as anything that occupies space and also has mass. And it's easy to identify matter that we can see. It's a little trickier on the stuff that we can't see, right? Like something like air, we can't see it. So we went over that. We talked about molecules and atoms. We did get into single arrangement of atoms here, isopropyl alcohol. Okay. The 3 states of matter, yeah, so we did talk about when defining matter, we can classify it as a solid, liquid, or a gas. There is another state of matter called plasma, but we, for the sake of this class, are going to stick with solid, liquids, and gases. Water is super cool. Not only is it, essential for life, but it also serendipitously at room temperature on Earth can exist as a solid, a liquid, and a gas. So when we're talking about the difference between a solid, a liquid, and a gas, the properties of those will shift. The material itself is the same, like water, for instance, H2O. Whether it's a water liquid, whether it's ice as a solid or a gas, it's still only composed of 2 hydrogens and an oxygen. But the way that those molecules are kind of buddied up or arranged with their surrounding neighbors will shift its phase and its properties. So if we look at ice, in ice, the water molecules are closely spaced, and although they vibrate, so there is a little bit of what we call kinetic energy or vibration, they do not generate enough movement that they would actually roll past each other. So ice or a solid in general, for any material that's a solid, you can kind of think of it as like soldiers in a row. And maybe they're linking arms with each other. They're not bonded to each other, but they're sort of fused in space to each other. Liquid, on the other hand, how do we go from a solid to a liquid? There's a couple different ways, but one of the simplest ways to understand is we add heat, right? So if you have ice and you put it in a pan and you put it on the stove, what are you doing? You're putting energy into that system. You're putting energy into that ice cube, and those water molecules that were at one point lined up like soldiers in a row, they now start to vibrate, okay? So you can almost think of like you've given those soldiers like, I don't know, like a keg, and they've got a bunch of energy now, and they're starting to vibrate and move past each other. And so now they're still close together, but they're free to move past each other, which is what gives it that fluid or flowing quality. If we pump a lot of kinetic energy in, like a good amount, we can move into what's known as steam. And those particles now, the water molecules, are vibrating so fast that not only are they were rolling past each other in the liquid form, but now they have so much energy that they want to get as far away from each other as they possibly can. They want to occupy a bunch of space and expand. And that's when we move into a steam or a gas form. So here's a visual of those three things. This thing is always in the way, isn't it? So here's our solid ice form. So we've got all of our little water molecules. They're all pointed in the same direction. There's a little bit of vibration, but not enough to break this crystalline structure. We add a little bit of energy, and we now move into a liquid form. We can see the particles are still very close together. That's important. They're close together, but they're no longer lined up in a row. Now they're sort of flowing and dancing past each other. And then if we move into a gas, these guys, not only are they dancing, but they are getting really, really hot, and they don't want to be right next to each other because they have so much vibrational energy. So when looking at a solid, atoms or molecules are packed close together and they have a fixed location. Neighboring atoms or molecules in a solid may vibrate or oscillate, so there is going to be some movement, but it's not enough for them to move past each other. Now this is a new thing here. Solids have a fixed volume, and then they also have a rigid shape. So examples: ice, diamond, quartz, iron. I'm sure you can come up with a lot more. But when you take an ice cube out of the ice tray and you put it into your glass, the ice cube does not change shape, and it does not change volume, right? It doesn't expand or contract, and it doesn't move into a new shape, unless, of course, the ice cube melts into a liquid. Now, when it moves into a liquid, it'll have a different set of properties. Two different types of solids. So we have a crystalline solid. This is what you think of when we looked at that ice cube, or look at like NaCl, salt. It's when all the atoms have this sort of long range geometric order to them. So it's those soldiers lined up in a row. An amorphous solid, on the other hand, does not have long range order. In an amorphous solid, we'll see like certain areas maybe are arranged in one way, and then in another way, the soldiers are pointing like a different direction, but they're still really close together and they're fixed. This would be, some examples of this would be like glass, rubber, all those plastics, all those sorts of things. They're keeping a rigid shape, but their molecular alignment is not as ordered. I think the next page has sort of a visual. Yeah, so here we've got, you know, very strict soldiers here. They've made it, they're standing still, but they're sort of all pointing different directions. There's a nice crystalline solid. So sodium chloride is our sort of basic go-to salt. We've got a sodium stacked next to a chlorine, stacked next to a sodium, next to a chlorine, so on and so on. We get this long range order. And the thing that's really cool about the microscopic, or the tiny, and the macroscopic, or like the larger scale, is that what you're seeing on a microscopic scale, we start to see expressing itself on a macroscopic scale. So with something like salt, right, they have this very ordered structure that makes this sort of cubic shape. And then on a big scale, crystals will also grow in a cubic shape. Different than when we're dealing with something like rubber. We have the ability to morph and change rubber into different shapes. So let's say we've added heat and we've moved into a liquid form. So in a liquid, atoms and molecules are still very close together, but these guys are able to move past each other. So adjoining molecules and atoms have the freedom to flow. So because of that fluid or free movement, liquids have a fixed volume. I can't change the volume of a liquid because they're close to each other, but liquids can change their shape and assume whatever container they're in. So if I have a water bottle and it has 50 milliliters of water, and then I take that water and I pour it into a graduated cylinder, it's going to show that it has 50 milliliters, but the water itself has changed shape, right? It's gone from sort of a wider basined water bottle to this really narrow graduated cylinder. So volume, same, shape changes. Water, gasoline, alcohol, and also mercury. Mercury is the only metal that we deal with that is liquid at room temperature. So this talks about it. Yeah, we'll get into compressibility with liquids in a sec. So as far as gas is concerned, you've got to pump a lot of energy in to get something into a gaseous form. Think about taking an ice cube. You've got to turn your stove up pretty high to get that ice cube to turn to a liquid and then to boil. There's some things that you've got to get really, really hot to turn into a gaseous form. Like if we look at something like iron or sodium, these things, we need heat levels that we find inside a sun to vaporize or gaseous those. But in a gaseous form, if we're dealing with something like water, so we've heated it up, and now the molecules or atoms, they have so much energy that they're going to separate from each other in large distances, and they're still going to be free to move past each other. So because these atoms and molecules take up so much space, or they're so far away from each other, or they're not in contact with each other, gases are the only one of the states of matter that are compressible. So I can take a gas and I can shrink it down into like an oxygen tank, or I can open that oxygen tank and let that oxygen fill up the entire space of a room. Gases will always assume not only the shape of their container, but they will also assume the volume of their container as well. So if I have a little vial of oxygen and I dump it into a room, that vial of oxygen will not only pour itself into the room, but then it will expand until it has distributed itself evenly throughout that room. Oxygen, helium, carbon dioxide are all examples of gases at room temperature. So let me move this up here. So gases are compressible. Here's a gas. Lots of empty space in our gas because these things are so far apart. So we have the ability with energy to compress a gas down. Solids, we're not going to be able to compress them. There is not enough space. So this is a good chart to know. You will get asked some conceptually based questions on the exam just about like solids, liquids, and gases and what their shape and volume changes are and their compressibility. All right, so when we talk about the universe, we can sort of divide it into matter and energy. And if we're dividing it into matter, if we've classified it, okay, this is not an energy thing, this is a matter thing. It takes up space and it has mass. We're then gonna wanna distribute that or define that into two different things, either a pure substance or we're going to classify it as a mixture. Okay, so there's a flow chart all the way back here that sort of talks about this. All right, so we start off with matter and we can divide it into either a pure substance or a mixture. So if you want to write those out while we're lecturing, you can, it might help you. So what is a pure substance? A pure substance is composed of only one type of atom or molecule. So hence being pure. So like an aluminum can would be a pure substance. When they're talking about one type of molecule, rubbing alcohol would be an example of a pure substance. It contains only isopropyl alcohol molecules. So a pure substance does not just include one type of element, but it includes one type of atom or one type of molecule. A mixture, on the other hand, is composed of two or more different types of atoms or molecules. And the key thing here with a mixture being that you can vary the proportions. So with a pure substance, if it's aluminum, it's only aluminum. If it's water, H2O, it's 2 hydrogens for every 1 oxygen. That's the recipe. It has a specific formula to represent it. In a mixture, these two things that are mixed together, not bonded together, the 2 molecules or the 2 atoms or atom and molecule, we can shift their proportions. So let's spend a little bit of time here with pure substances and then we'll get back to mixtures. So in a pure substance, I'm going to hop forward just for a second here. I can divide a pure substance into either an element or a compound. Okay, both of those are examples of pure substances. So an element is a pure substance that can't be broken down into anything. It says simpler substances. Really, you can't break it down into any simpler identifiable substances. I could take carbon and break it down into protons and neutrons, and I could take hydrogen and break it down into protons, but the protons from carbon and the protons from hydrogen are going to be the exact same. So I can't really break it down into anything simpler that has a unique stamp to it. So no chemical transformation can decompose an element into a simpler substance that's identifiable. As far as elements are concerned, all the known elements are listed on the periodic table. So where to find a periodic table, that's on the inside of your textbook. Also the back of your lab manual will have a periodic chart. So you want to get that buddy out in the next week or so, okay? If you don't like the periodic chart that's given to you in your lab manual, that's fine. Go find a different one or print one off of the internet. But you definitely need to have a periodic chart available to you on a regular basis as we move forward in class, because when we're doing example problems and stuff like that, we're going to be using numbers from the periodic chart. And chapter 4 is when we talk about the setup of the periodic chart, but definitely get yourself one of those soon. Okay, so classifying matter. So helium, if we have a balloon filled with just helium, we would say that would be a pure substance. So these helium balloons are filled with just helium atoms, ideally, in order to make them a pure substance, and specifically an elemental pure substance. Compounds, which sometimes get mixed up with mixtures, so we don't want to do that. Compounds are a type of pure substance, and they're composed of 2 or more elements. The key thing here being that they're in fixed definite proportions, so that they have a chemical formula to them. So in order, so an example of a compound would be water. And water is H2O. That is its defining quality. I need to have 2 hydrogens bonded to 1 oxygen. In general, compounds tend to be more common than pure elements, because elements by themselves, like aluminum or sodium, or really most of the things on the periodic chart, they're kind of unstable alone. Just like us as people, we're kind of, I mean, not everybody, but some of us are a little bit more unstable. We do better when we're in a relationship or in a community. So we bond together with other people. Elements do the same thing. Most elements are chemically reactive, so they combine to become more stable or less reactive. So examples of compounds: water, table salt, and sugar. Anything that can be written with a chemical formula is an example of a compound, right? So CO2, CO, carbon monoxide. SO4, SO3. Okay, all these things that I can write out with the chemical formula, I'm going to say are compounds. Compounds are a little different than elements in that compounds can be decomposed. So they can be decomposed into a simpler substance. They can be decomposed into the elements that they're made up of, right? So carbon, or rather CO2, can be broken up into carbon and oxygen. So we could, through some sort of chemical process, break these two things apart. Water, there we go. So this water here we're assuming is a pure substance. Probably, if this is coming off of a water fountain or some sort of spout, it's probably not a pure substance because it has a bunch of contaminants in it, or other different things that they put in water. But let's say that this is deionized water, so pure water here. So let's talk about the difference between a compound and a mixture. So this here, compound, and mixture tends to get a little bit mixed up. We want to make sure we keep those two concepts separate. So when matter contains two or more atoms, it can be a pure substance or it can be a mixture. If it is a pure substance, it would be a compound. So we have atoms bonded together in a fixed, definite proportion. A mixture, on the other hand, is composed of different substances that are not chemically bonded. They're not chemically bonded, or they're not united, and they're just simply mixed together. So let's look at this scenario at the beach, which would be so awesome to be at right now, right? We've got the water, we've got the air, and both of these, water, seawater, and air, are examples of mixtures. They contain compounds, but they themselves are a mixture. So what is the mixture that's occurring in the water? Well, salt water or seawater contains H2O molecules, but it also contains dissolved salt in it. So depending on where you are, if you're closer to the equator, you'll have more salt than if you're maybe closer to the poles. So this can shift or change in proportionality. You've ever been in an area where you have brackish water, where you have salt water and fresh water mixing together, we can sort of dilute the amount of salt that we have in it. So anytime I can change proportionality of these two things, we're going with a mixture. As far as the air is concerned, same thing. So air is a mixture of nitrogen, oxygen, there's also some argon in there and some trace things, CO2 and methane. But I mean, for the most part, those are consistently mixed throughout the whole atmosphere, but we could potentially have an area where there's a little bit more nitrogen than there is oxygen, or vice versa. So a pure substance can be either an element or a compound. Now, when we're dealing with a mixture, if we're going to distribute that out further, classify it further, we're going to talk about being either a homogeneous, or sometimes people say it, a homogeneous mixture, and then a heterogeneous mixture. So a homogeneous mixture is a mixture that's evenly mixed throughout. So an example would be sweet tea. So if you add sugar to your tea and you give it a good stir, you're going to find that unless you've completely saturated it with sugar, the sugar content at the top of the teacup should be the same as at the bottom. One way to remember that is homo being the same, root for being the same. So homogeneous, the same throughout. Now, a heterogeneous mixture, an example would be hydrocarbon and water. Don't get scared by hydrocarbon. That would be like oil and water, okay? So, or oil and vinegar. So when we've got oil and vinegar, those things don't really mix well together. They always sort of pull away from each other. So in a heterogeneous mixture, your mixture will, your proportions will change depending on where you're sampling it. So if I have oil in water or oil in vinegar, I will find that the oil is highly concentrated at the top and that the water or vinegar is highly concentrated at the bottom. So here is that whole thing stuck in one chart, which is super helpful. So we've got pure substances, element, compound, homogeneous, and heterogeneous. So I'm going to give you guys a couple examples, and I want you to classify them as elemental, compound, homogeneous, or heterogeneous. All right. Actually, let's go back to. Okay, so sulfur dioxide, bananas, and oatmeal. A can of Coke. Gold ring. Okay, so go ahead and classify these based off of what they are, what kind of matter you would say they are. Okay. So for this first one, sulfur dioxide, this is a chemical formula. You will learn a little later on in the semester that this is specifically SO2. It's got a specific recipe. Okay, so I can't vary the amount of sulfur and I can't vary the amount of oxygen. So we're going to say that this is a compound. Bananas and oatmeal. That definitely sounds like a mixture. Okay, then we just need to talk about, is it heterogeneous or is it homogeneous? Well, I know that when I have bananas and oatmeal, the first couple bites of mine tends to be a lot of bananas with a little bit of oatmeal. And then towards the end, I just get all the icky oatmeal. So my bites aren't consistent. And that means that we've got a varying mixture capacity with this. So we're going to say that this is a heterogeneous. Coke. Okay, so Coke is a mixture of water and high fructose corn syrup and a bunch of other garbage. But that garbage is evenly mixed throughout, isn't it? So we're going to say that this is a homogeneous mixture. Okay, but I'm not going to lie, every now and then I do like to have a Coca-Cola. That's good. All right, a gold ring. Well, hopefully that ring that whoever gave you, like, it's pure gold. We're going to say it's a pure gold ring. So that is going to be an element. Anytime it's, aluminum, gold, mercury, oxygen, specifies it as just a single element, you can say it's elemental. Cool. All right, so we don't need to summarize it. I feel like we got that now. So when looking at matter, matter, depending on what it is, right? If it's water, if it's zinc, whatever it may be, we can have different physical and chemical properties. Is O2 considered a compound? All right, so O2, we would call that an element, but we specifically call it a diatomic element or a molecular element. We wouldn't put it under the compound category, we would put it under the element category. And we will talk a little bit later about why oxygen is O2. There's like 6 or 7 elements that like to be buddied when they're in elemental form. Good question, but keep that one under the element, yeah. All right, so physical properties. So when we're describing a physical property of matter, it's something that the material can display or show us without having to change its composition. So a physical property could be its density or its color, right? If I look at a gold ring and I'm like, oh, it's kind of metallic yellow. It doesn't have to become something new in order to express that property. A chemical property, on the other hand, is something that a material can only show you through changing its chemical composition. So flammability, like gasoline is really, really flammable, right? The only way that you can measure its flammability or see that property of its flammability is by lighting it on fire. And then what is going to happen is it's going to combust and we're going to get CO2 and H2O. So we end up finding a new material at the end. So here, like odor of gasoline. So when you smell gasoline, I don't recommend doing that on a regular basis, but if you're filling up your tank and you get that smell on your hands, that's a physical property of the gasoline. Nothing has changed in order for the gasoline to be smelled. The only thing that's shifted is the gasoline has turned into the gasoline has turned from a liquid to a gaseous state. It's volatilized, so that it then can enter your nose, and then the little receptors are getting pinged by the gasoline in your nose. Now the flammability, right, we would need to actually burn it. We no longer have gasoline. That's what your car does. It combusts gasoline and it spits out CO2 and H2O out of the back of your car. So do note physical change of water. So whenever we're changing states, so if we're going from a solid to a liquid or a liquid to a gas, or even if we're going from like a gas to a solid, we're doing sublimation, any of those things, those are all physical properties, okay? So water's boiling point is 100 degrees Celsius. That would be a physical property because water doesn't have to become something new in order to boil. It just changes its phase, all right? Liquid water, H2O. Steam, still made of H2O. Haven't changed what it is. So there's a good image of it, why this is a physical property. We're heating it up. Look at that, there's a bunch of H2Os. The only difference between these H2Os and these H2Os is that these guys are packed closer together. These guys have more energy and they're farther apart. So state changes, transformation from solid to liquid, any of those are all considered physical changes. And that can be a little tricky because sometimes physical changes can look kind of crazy, like iodine, for instance. If I take solid iodine, it's this sort of metallic, dull metallic solid. When I heat it up, it will vaporize or turn directly into a gas, and the gas is pink. And so it can look, oh my God, I've done some sort of like chemical magic here, but you haven't, you really just shifted its phase. So these slides start to get a little redundant, but in a physical change, matter changes its appearance, but not its composition, okay? So when ice melts, it looks different, but it is still made of H2O. In a chemical change, matter will actually change its composition. So when we have copper and it starts to patina, or it starts to turn green, the reason that's happening is because the copper has combined with oxygen in the air to form a copper oxide. And that's what that greenish color is. So we have a new material. Same thing with rusting on a nail. So this would be a chemical property. So the unrusted part is just iron atoms, but these guys are relatively unstable. So when they're exposed to oxygen in the atmosphere, they will grab oxygen out of the air and fuse it together to form this new iron 3 oxide, or an iron oxide. So if a chemical change has occurred, you can write a chemical reaction. And this is, we're going to keep it really basic for this chapter, but this is how a chemical reaction would be set up. So we have reactants on one side. We have an arrow that represents its chemical change, and then we'll have products on the other side. So reactants to products. So I'm going to give you a really simple one here. Let's do methane. And again, don't get scared of the details of this. I don't expect you to know these compounds yet or anything like that, but methane, CH4, combines with oxygen to produce CO2 and H2O. Now I'm going to throw a 2 here to balance this. I'm going to throw a 2 here to balance this. Again, we will talk about that later on in the semester. Don't worry about it now. But what I want you to see is that these guys here are acting as the reactants. We have 2 reactants. These guys over here are acting as the products. We have 2 products. Okay. The arrow in the center is that point of flammability when it changes. These slides keep going. Okay, chemical changes. So the difference between chemical and physical changes, you can see it on the molecular level. Yes, so in physical changes, the atoms or the molecules do not change their fundamental associations. In chemical changes, the atoms will change their fundamental associations, meaning that they'll change partners, they'll rearrange who they're grouped to or how they're grouped to. If we had like really awesome like mass spectrometer eyeballs, we could see if it's a physical or chemical change really easily, but we don't. Here's a butane lighter. If you've ever, messed around with the butane lighter and you've just pushed on the plunger, you didn't strike it, you just pushed on the plunger, the butane will seep out. You may even be able to smell it. What's happening here is we've got liquid butane now turning into a vapor of butane or gaseous butane. This would be an example of a physical change, right? As long as you're not striking it, if you're just opening the plunger and just letting this out, you're just volatilizing it. Physical change. So we're not going to talk about physical changes. This is missing one. Oh, there it is. Okay. Yeah. So if instead of hitting the plunger, you strike the flint and you hit the plunger at the same time because you need to light something, that will be when you are creating a chemical change. So the butanes, the cute little butanes in there, are being combusted and they are now turning into CO2 and H2Os. So we have actually different things coming out of our butane lighter. So as far as, I guess we'll talk about it really quickly, but as far as if you have a mixture, there's a couple different ways that you can separate out mixtures. Like if we had, let's say we had salt water. One way is this process of distillation. So you can take let's say we've got salt water here. You can take your salt water, you can heat it up. And what will happen is that the water will evaporate. The salt will be left behind. You can put it through like some sort of condenser with cold water and then collect the water over here. So now you'll have water here, ideally pure water here, and salt over here. This is, one reason here. This is why desalinization is not the solution to our water shortage problems, because what do we have to do in order to separate water from salt in this scenario? We have to heat it up. So we have to use a fossil fuel. And water has a very, very high heat capacity. So we actually have to use quite a lot of energy to separate these two things out from each other. So desalinization, at least through distillation, is not really practical unless you live like in the United Arab Emirates or somewhere in the Middle East where you're a very wealthy country with a lot of fossil fuels for your excess. They do desalinization pretty well. Another way to separate mixtures is through filtration. This is usually, you'd use this if you had like a solid and a liquid mixed together. So we could take the solid liquid, pour it through some filter paper. The liquid will pass through the filter paper and the solid pieces will stay left behind. So if you had like some muddy water, you could use filter paper and that would go ahead and get the solid stuff out for you at least. It might not get all the microbes out, so I wouldn't take dirty water and pass it through filter paper and then drink it. You would probably need to do a secondary purification in order to drink it to get bacteria out. So now on to this concept called the law of conservation of mass. So there is no new matter in a chemical situation. So matter is neither created nor destroyed in a chemical reaction. So whatever you're starting with is what you're ending with. So if you have 55 grams of something and you, let's say we have 55 grams of aluminum oxide and I break it up into aluminum and oxygen, the total mass of the aluminum and oxygen better also be 55 grams. Now, this law of conservation of mass does not apply to nuclear reactions. In nuclear reactions, which we don't go over in 092, but you will talk about, I believe, in 151, or if you take 130. In a nuclear reaction, you can get a big shift in mass because you can take mass and convert it into pure energy. That's what's happening in like a power plant or in a nuclear bomb. We're taking a relatively small amount of mass and we're converting it into a big amount of energy. So let's look at this here. Here's a chemical reaction. Here's a problem. It says, suppose that we burn 58 grams of butane in a lighter. It will react with 208 grams of oxygen to form 176 grams of carbon dioxide and 90 grams of water. So if I was to have you write out a chemical formula for this, or a chemical equation for this, you don't even need to know the formulas. You can literally just write, okay, what's happening? Butane is being added to oxygen. Anytime you see the word to form, to produce, to create, to decompose, that is the change point. That's your arrow, right? So that's separating your reactants from your products. So we have butane combining with oxygen, and we're producing carbon dioxide and water. And it gives us the total amount of each of these. We have 58 grams of the butane, we have 208 grams of the oxygen. And this problem specifically, it's not really a problem, but it says it has 176 grams of carbon dioxide and 90 grams of water. Let's say I had left out the amount of water and I wanted you to calculate the amount of water. You could do that pretty easily with just some basic math. Because if we know what the butane mass is and we know what the oxygen mass is, we can figure out the total amount of our products. It should be 266 grams. If our products are equal to 266 grams for the sake of this class, because we aren't doing nuclear chemistry, if the reactants have a mass of 266 grams, your products also need to equal 266 grams. Those have to add up to each other. Because if in chemical reactions, matter just sort of randomly disappeared or appeared out of nothing, that would be a very strange universe that we live in. All right, so the last thing that we're going to talk about is energy. So when we're talking about the universe, we divide it into matter and energy. Hopefully you're pretty good with matter now. The driving force behind matter is energy. So the reason that like all this matter is interesting, that it's not just these sitting blobs frozen in space, is because they have energy, right? So water flows because of energy. Our bodies move because of digestion of energy. And so as far as energy is concerned, energy is the capacity to do work. And I don't mean work in like your job sense, but I mean, your job does require energy, right? You have to go to work and move your body and use your mind. And in order to do that, you need energy, and where you get the energy from is food and things like that. But when I'm talking about work in a more science-based way, it's defined as the force acting over a distance. And so the behavior of matter, or how matter, what it does, what makes it interesting, is all based off of the type of energy it has, or how much energy it has. And you have to know and understand energy in order to understand chemistry. And most of this class we will spend talking about matter. We talk a lot about matter, but we do need to have some understanding of energy to get through the course. So just like there's the law of conservation of mass, there is a law of conservation of energy as well. And this states that energy, just like mass, is also conserved. So we can't create or destroy energy. The total amount of energy that's out there in the universe is constant. It's simply being changed from one form to another, or it's being transferred from one object to another. We can't create or destroy it. We can't make it out of nothing. And we can't stuff it into nowhere. That's why a perpetual motion machine is not a realistic option for us, because we can't just make energy out of nothing. There has to be something there to make that energy. So an example of this sort of transfer of energy, right? This morning I ate, well, I didn't really eat anything this morning, but last night I had like some banana pudding. So that banana pudding, while I was sleeping, yeah, it's Paula Deen's recipe. It's like really, really good. If anybody wants it, I could email it to you. Because it's not enough just to have banana pudding. You have to put an entire container of cream cheese and a can of condensed milk in it just to take it to the next level. But I had that last night. So while I was sleeping, my body did a really cool thing. It took that food and it broke it down into energy into my body. And specifically, it broke it down into stored energy as sugar and fat cells. So then I woke up, I had to get up, I had to wash my face, I had to get dressed, I had to use that potential energy stored in my body to do physical actions, right? Or kinetic energy. And then I'm sitting down here right now talking to you guys, not physically using a lot of energy, but mentally, you know, we're all using a lot. Hopefully we're using some energy in the brain. And that again is a transition of stored energy into movement of neurons and chemicals and things like that in the brain. So as far as the different types of energy, kinetic energy is energy associated with motion. So kinesiology, someone that studies kinesiology, they study movement, right? They tend to be like athletic people. So you running into a brick wall is a type of kinetic energy. All right. Potential energy is energy associated with position or its composition. So fat cells are a type of potential energy. They're in your body. They have a lot of stored energy in them, and we use them. If we don't use them, then we just end up with a lot of stored energy on our bodies. Composition is another thing that can set up something with potential energy. So like outside of fat cells, like TNT, for instance, okay? TNT has a lot of potential energy in it because of the way that the atoms are arranged. It wants to explode versus water, which has a lot less potential energy. And then position-wise, if I have a pen and I raise that pen up, I'm using kinetic energy, well, I'm using potential energy in my fat cells, turning it into kinetic energy to lift the pen up. This pen, when it sits higher up off the surface of the earth, has a higher potential energy to it. Same thing with like a spring. If I take a spring and I compress it, I'm taking my kinetic energy and I'm putting it into potential energy into that spring. We've also got electrical energy, which scares me and I don't know a whole lot about. Physics was never my thing. So I know a little bit about electrical energy, but not a whole lot, but it's associated with an electric charge. Thermal energy, which we like a lot, we use that a lot here in chemistry, is the energy associated with the random motion of molecules and matter. So thermal energy you can think of as like temperature. So if you increase the temperature of something, those particles in it have more random motion. And then chemical energy is a form of potential energy associated with position of particles in the material. So TNT has a lot of this chemical energy. So what is the unit that we use for energy? The SI unit is the joule, capital J, after James Joule. A second unit of energy that we will use is a calorie. And calorie is, there's two calories, okay? There's little c calorie, and then there's capital C or big C calorie. Big C calorie is the nutritional calorie. That's the one that you're thinking about on the back of your candy bar or your food boxes. That's the big C calorie. Little c calorie is something different. Little c calorie is the amount of time, the amount of energy required to raise 1 gram of water, 1 degree Celsius. So a calorie is going to be a lot bigger than a joule, and then a big C calorie is actually going to be 1,000 times bigger than a little c calorie. Sometimes the big C calorie is called as a kilocalorie because it's 1,000 of them. We're not going to do a whole lot with the kilowatt hour, but this is something that they use like in your household electrical bills. It's measuring how much energy you have over a given time. So the kilowatt hour. But let's go here to the next slide. So these are some of your conversion factors for energy. So again, we're not going to spend a whole lot of time with kilowatt hour, but definitely want to be able to do calorie to joule and big C calorie to little c calorie. So 1 little c calorie is equal to 4.184 joules. And that number is going to pop up again. That 1.4 or that 4.184 will pop up again. And then a big C calorie is equal to 1,000 little c calories. So let's do a conversion dimensional analysis problem with these. I'll write them on the next page here too. What are you doing? Okay, so how many joules are in a candy bar with 356 big C calories or nutritional calories? And I'll write, so 1 calorie is equivalent to 4.14 joules. And then 1 big C calorie is equal to 1,000. Just another 30 seconds. Okay, so I'm looking at this problem, and if you were to be given something like this on a test, these here may not be written right underneath the problem, sort of guiding you in the right direction. So you will need to reference a formula sheet. There is a formula sheet in your lab manual, and I will also post a formula sheet up on Moodle for you guys before your first exam that'll have like easy access to different conversion factors. So you've got to sort of think, okay, I've got my given is that I have 356 big C calories, and you want to make sure you're keeping the big C and the little c separate. And I'm trying to find joules. So I don't have off of my formula sheet or right off the bat, like a direct relationship between those. So I'm going to do a two-stepper here. So I'm going to go from big C calories to little c calories. And then little c calories, I'm going to hop myself into joules. So start with my given, which is the big C calorie. I've got 3, 5, 6 big C calories. And I'm going to multiply it by the first one that makes sense. So if I want to go from big C calorie to little c calorie, I want to use this one here. So I need to situate it in such a way that the big C goes on the bottom and the little c goes on the top, right? Because you want to get from these units into these units. We're not even going to worry about joules yet. So on the bottom, for every 1 big C calorie, I end up with 1,000 little c calories. So those will cancel. Some people like to stop and solve. I'm going to stitch them together. Next one is to go from little c calories into joules. So that's when I'm going to use this bad boy here. Now the little c calorie, instead of it going on the top like it did here, it's going to go on the bottom here because I want those two to cancel. So for every 1 little c calorie, I get 4.184 joules. So this will cancel with this. When you plug that into your calculator, you get a relatively large number. You get a lot of joules in a candy bar. Maybe we'd eat less candy bars if we represented it in joules instead of calories. So I've got sorry, my daughter is screaming bloody murder out there. 1, 4, 8, 9, 504 joules. This is what the calculator popped out. Now we're limited to 3 sig figs here, okay? So we keep the 1, we keep the 4, and we keep the 8. 1, I'm gonna write in scientific notation, 1.49 times 10 to the what? 1, 2, 3, 4, 5, 6, 10 to the 6 joules. 1.49 times 10 to the 6, sorry, 1.49 times 10 to the 6 joules. Okay. Don't get freaked out by this. It's just scientific notation. Written in scientific notation. All right, so we're only going to do one of those because at this point I hope that your dimensional analysis, so you're starting to hone that skill. Goodness. Does everybody feel like everyone in their family or house is just like 2 seconds away from a full-blown meltdown at all times? The only ones who have it together are dogs. My dog's got it together. Okay. Great. So we've got those units. Oh, here's a candy bar problem. We already did a candy bar problem. Okay, so you can go ahead and redo this one later if you want to practice it. So potential energy. So again, we've got a weight. If we take that weight, let's say the weight's sitting down here somewhere, and you have to carry it up the stairs to the top. You are using potential energy in your fat cells to move it into kinetic energy to lift this weight up. Now it has a lot of potential energy. It's highly unstable. If it falls, it changes its potential into kinetic energy. And then as it hits the ground, this is kind of cool, it changes, because if you wonder, well, it just stops, right? It just stops at the earth. Then it's, where did the energy go? Well, the energy actually turned into heat or thermal energy. So this kinetic energy then turned into heat. So the ground underneath this weight will actually just get ever so slightly warmer. And if you're thinking, well, I don't really believe that that's happening. Okay, well, let's take a bigger object moving much faster. Let's take a meteor and shoot that at the earth. What happens? We get a huge production of heat where the explosion is. So this, you can kind of think of this as like a mini meteor, just not from as far away or as fast. We already talked about potential energy based off of materials, like how the atoms are organized. So some chemical substances like TNT have a relatively high potential energy concentrated in them because of the way that their atoms are arranged. They're unstable. So this wants to rapidly undergo a chemical change so that it can lower its potential energy. Things that have high potential energy want to lower their potential energy for the most part. Tends to be the case. So when looking at a chemical reaction, we can classify chemical reactions as either exothermic or endothermic. An exothermic reaction, exo, think of exit. That is when a reaction releases energy into the surrounding environment. So here, this A is an example of an exothermic. We have reactants. They have a lot of energy, right? If we look at this, this is high energy, this is low energy. So we have reactants, and then they release energy to produce your products. So the products have a lower energy than your reactants. This is what we see a lot with like combustion and things like that. So our gasoline has a high stored energy, and then we combust it, and the products, water and CO2, have a much lower energy. But these reactants, how did they become higher energy? Well, they had to have undergone what's known as an endothermic reaction. So endothermic reactions are the opposite of an exothermic reaction. In an endothermic reaction, the material, the reactants, absorb, or they take energy from their surrounding environment so that their products become higher energy. Rule of thumb, exothermic reactions will feel warm to the touch. Endothermic reactions will feel cold to the touch. So if you've ever injured yourself and used one of those like ice packs, not the ones that you've frozen, but the ones that are room temperature and you have to break them. There's like a little container on the inside and you break them, and then all of a sudden they start to get cold. It's because there's a chemical reaction. So the two chemicals are mixing together. That thing is now creating an endothermic reaction. What that thing is doing, that pack, is it's sucking heat from the surrounding environment. So when you put it on your knee or your elbow or whatever is injured, it's literally sucking heat from your body to try and create a cooler environment that has less inflammation to it. Chemistry, it's everywhere, all over the place. Can't live without it. I mean, you can live without knowing about it, but you can't live without it. So talking about temperature and thermal energy, so the atoms and molecules that compose up matter are in constant random motion. So every piece of matter, there's a little bit of vibration to a lot of vibration that's happening that we classify as thermal energy. And when we measure something's temperature, all we're doing is measuring its thermal energy. So we're just measuring how much it's vibrating. So when you say, oh, it's 72 degrees outside, it means that the air is vibrating at such a way that it's allowing your thermometer to read 72. When it's colder, the air in the is now not vibrating as much, and maybe it's vibrating and saying that it's 52 degrees out. So the hotter the object is, the more we get this random motion. That's also why as we heat things up, they tend to phase change from solid to liquid and liquid to gas, because they're getting more of this thermal energy. Now, heat is a different concept. Sometimes people will confuse heat and temperature. Temperature is a measure of the thermal energy of matter. So like if I was to measure the temperature of a pan, I would be measuring how quickly those atoms of, let's say it's a copper pan, how quickly those atoms of copper are vibrating. Heat, on the other hand, is measured in a unit of energy, and it's the transfer or exchange of thermal energy caused by a temperature difference. So when a piece of cold ice is dropped into a cup of warm water, the warm water transfers heat or thermal energy to the ice cube, and then it melts it. So that transition or transfer of energy we call heat. Temperature is sort of frozen to the object that we're just one object that we're specifically looking at. So some measurements of temperature, we use Fahrenheit here, which again, will like not the most useful scale, but it is what it is. So on the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and it boils at 212 degrees Fahrenheit. Why don't they just have the Fahrenheit scale where water freezes at 0 degrees Fahrenheit? I don't know. This is a specific amount, specific homogeneous mixture of salt water, what it will freeze at. And that's just what they went with. Celsius, much more useful. Celsius, which is what they use pretty much everywhere else, is also measuring thermal energy, but on its scale, water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. Nice and convenient, so you want to know those. On Celsius, room temperature is approximately 22 degrees Celsius, which is a little weird to wrap our head around in our Fahrenheit world, because when we hear 22, we think, oh, very, very cold, but that's not the case on the Celsius scale. Kelvin, Kelvin is directly related to Celsius. These two guys are real easy to shift between. If I want to go from Celsius to Kelvin, all I do is add 273. And what the Kelvin scale does is it avoids having any negative temperatures. So the coldest temperature in the universe, or absolute zero, is 0 degrees Kelvin. You cannot get colder than 0 degrees Kelvin. Why? Because what is temperature measuring? Temperature is measuring the random motion of atoms. And when we've reached absolute zero, this temperature, all molecular motion will virtually stop. You can't have a negative stopping of motion. We just have an approach to that. We actually don't ever really approach or ever actually get to absolute zero. We just sort of approach it, right? So we get close to that point where all the molecular motion stops. So Kelvin is really useful later on when we get into gas laws and stuff, because we don't like to have negative numbers when we're doing calculations. It doesn't work for us. So real easy to shift between these two, just add or subtract 273. So water freezes at 273 and water would boil at 373. Here are the calculations to get from Kelvin to Celsius. You just add 273. This is to get from Celsius to Fahrenheit. It's a little bit more complicated and sticky. Again, this will be on a formula sheet for you all when you take your test, but you do need to be able to transfer between Celsius and Fahrenheit and Celsius. It's literally just plugging into an equation. So why don't we do one? Okay, it is 80 degrees Fahrenheit outside. I want to know what that is in Celsius. And why not? Okay, I want to know what it is in Celsius and then tell me what it is in Kelvin as well. Given 88 degrees Fahrenheit. I want you to find this in Celsius and Kelvin. And it is literally as easy as plugging it into that equation. Okay, so if it was 88 degrees Fahrenheit, a really nice hot day, but let's say we were in France or Germany, they would say 31 degrees Celsius. Okay, 31 is a warm temperature for them. If we were to convert that to Kelvin, because let's say we had to run it through a calculation and we didn't want any zero, 304 Kelvin. Sig figs with temperature, I'm not going to be like super anal about. Okay, so don't stress too much about that. All right, so we've got 1 minute left, but I'm going to use it. Okay, so heat capacity. So what is heat capacity? Heat capacity is the quantity of heat, usually represented in joules, required to change the temperature of a given amount of a substance by 1 degree Celsius. Okay. We use, in this class, we're going to talk more about this thing called specific heat capacity, or sometimes it's called specific heat. The amount of a substance is expressed in grams. The heat capacity is called the specific heat capacity. And this is got a lot of funky units to it. It's joules per gram degree Celsius. And I'm just gonna move to the next slide real quick because it's got the formula for us. So this is the equation for specific heat capacity, okay? Q, I call it Q equals MCAT. Q equals MC delta T. We've got Q, which is our heat in joules, M, which is our mass, C, which is our specific heat capacity, and change in temperature, which is final minus initial, all right? We're gonna do a bunch of practice with that next week. It will be on your homework, so take a look at it. Hopefully you'll be pretty good with that. But it's really 4 variables, and you have to solve for you'll get 3 and solve for the 4th. That's not too bad. All right, so we'll leave it at that. That's it for the week, right? That's all I'm gonna see you guys for. So sad. I'll see you next week, okay, on Monday. If you have any questions, stay around and I can help you out. Otherwise, have a good week and weekend. I'll see you next week. Bye.
I have a quick question about this exam that's coming up.
Give me 1 second. I'm just gonna stop recording so that